Hello, everybody. Welcome to a new webinar hosted by Hiperbaric. Today we will be discussing about the potential of HPP for dairy products. And to talk about this topic, I would like to present my colleague Mario González. Hi, Mario. How are you doing?
Hi, Oscar. How are you? Good.
I'm ready to start with this session. All right. So. Okay, great. So just to share the background of Mario a little bit, Mario González is head of the HPP Applications department at Hiperbaric, where he coordinates the scientific and technological support tasks oriented to high-pressure processing users and potential users, of course. And he has more than 10 years of combined research and industry experience in HPP food science. Mario holds a bachelor's degree in food science and technology, a master's science in food biotechnology, and a Ph.D. degree in food microbiology. Just to share an overview of Mario's background. And okay, thank you, Mario. I think we'll see you later to cover the main topics and main assets of the session. Okay. So to start with the agenda, so that everybody knows what is going on in the next few minutes, to be more exact, in the next 60 minutes or so. I will start with sharing some fundamentals of HPP, explaining how this non-thermal technology works and its main benefits for those that are not familiar with the technology. Then it will come Mario's turn, and where he will be sharing scientific evidence on the use of HPP for dairy products, including shelf life extension for raw milk, HPP for different types of cheeses, and dairy product development innovations using HPP. And the final part could be 5-10 minutes, we'll see. We'll have a Q&A session directly with Mario, so please just start asking the different questions you may have regarding these topics. You have the chat on your screen, so I will leave a comment so that anyone can share their comments there, and Mario will take care of them in the Q&A session. All right, so I will continue with my part, which is the fundamentals of the technology of high pressure processing. So HPP is a non-thermal technology that just uses high pressure and water held for a few minutes and transmitted to the product, and the pressure is transmitted isostatically to the whole product, to every part of the product. And the main benefits of this technology is the control of pathogens and exfoliates microorganisms. And as a consequence, it offers brand protection against recalls. It also allows to develop minimally processed products and preserve the quality and nutritional profile of the products, since no heat is applied and you don't need to use any additives or preservatives. It also opens opportunities to access new markets due to the shelf life that you can gain to your products, and natural appeals, I already mentioned, without any additives. So to compare a little bit with traditional heat treatments, as mentioned, HPP is a non-thermal technology just using pressure, while pasteurization or sterilization use heat to preserve food. It's kind of HPP, I will mention it later. It has more than 2 decades having relevance on the food and beverage industry, but we can name it just as a new technology compared to the consolidated technology that are the thermal methods. Then pressure is transmitted instantly, and I will continue. I will connect this with the next one, and isostatically. That means that every part of the product is affected equally with the pressure, while in pasteurization there is a slow transmission of temperature, and therefore temperature gradients around the products. And with HPP, no changes can be found in the main composition of the products, while with heat and pasteurization, some formation of new compounds could be found. So let's continue. Yes, the quick picture of the evolution of HPP systems all around the world. So starting in 2000, you can see the great evolution that there have been. So with almost 700 systems installed worldwide, and with Hiperbaric having more than 400 units already installed in the 5 continents. And regarding the different HPP applications, it's a really versatile technology. It's also one of the benefits and advantages of this technology that can be applied to juices and beverages, meat products, guacamole and avocado products, seafood, salsas and dips, ready-to-eat meals, baby food, pet food, and of course, dairy products. But the thing is that we can say that only 2% of our systems installed are dedicated to the production of dairy products. But here we are in this webinar to trying to explain and serve the voice that HPP has something to say to the dairy industry, and is that the potential of this technology is huge for this sector as well. So some commercial samples that have been on the market or that are already in the market nowadays. Sorry. So different type of cheeses, raw milk, functional beverages like colostrum, you can see there on the image, some smoothies, dips and spreads, and also cold brew coffee with some milk, for example, just to give some examples in the market. And then to better understand how the technology works and the equipment, so traditional HPP equipment is impact, so that means that it applies to already packaged products in the final packaging. All right, but to better understand the process and how the pressure is applied to this final product in the final package, I would like to say one really short video so that everybody can understand the process.
Traditional HPP machines process in-pack products, generally in their final commercial packaging, are introduced in the vessel. The vessel is aligned with the yoke and is filled with low-pressure water. Then it is closed at both sides by plugs and wedges. HPP inactivates microorganisms without the use of heat, being respectful with the characteristics of fresh food products. Finally, the depressurization of the vessel and the opening of the machine take only some seconds. Afterwards, processed products are unloaded.
All right. I hope this short video helps to explain how our systems work. Talking about the impact range, which is commonly used for other products such as meat products and guacamole and many others that we already mentioned. So we offer the widest and most reliable range, with the smallest machine producing around 270 kilos per hour, and to the biggest one, Hiperbaric 525, that can process more than 3,000 kilograms per hour. So, but also I would like to mention that for this kind of equipment, that the pressure is applied directly to the products, is really important to have some considerations regarding the packaging. So being two of them, the most important ones. So being flexible and water resistant, since the pressure is applied through the water, these two elements are just key so that packaging can withstand the pressure and recover the initial shape. And this could be applied to bottles, bags, packing box, tubes, all the different packaging formats I'm showing right now in the screen, including cups, trays, and so on, being plastic or PET, mainly the principal material that make the packaging suitable for HPP impact systems. But I would like to also mention that we develop a global innovation, which is the HPP in-bag technology that allows to produce beverages using applying HPP, but in bulk prior to bottling. And this can give some different advantages that we will be mentioning later. And again, I would like to show another brief video that explains how these systems work so that you can tell the difference between the previous one, the impact, applying to already packaged products, and the input to input liquids prior to bottling. So let's go with the video, please.
Ready to process beverage is sent to the inlet tank of the machine. And from there, it fills the processing bag inside the vessel, occupying 90% of the total vessel volume. High-pressure intensifiers start pumping water inside the vessel around the processing bag, reaching up to 6,000 bar or 87,000 psi. Pressure is generally held for 2 or 3 minutes. Once the pressure is released, beverage is unloaded and buffered in the outlet tank. And then goes to the filling line, where any kind of packaging material or shape can be used.
All right. So, yeah, taking into account this process, the aim of developing this system was to increase the productivity for those industries, managing processing liquids. So with this system, you can process up to 4,000 liters per hour, thanks to the 90% filling ratio that it offers. It also has the lowest total cost of ownership, so by increasing production efficiency and reducing operator labor and minimizing energy consumption. So as you saw on the video, it's a completely automated process with no manipulation of the product. And it also offers packaging versatility. So while in HPP Impact we mentioned it had to be flexible and water resistant, here we don't have any limitations since the liquid goes directly to the filling line or bottling line. And then adaptation and automation, again, no handling of the product involved. And just to mention that we have one of these instances already installed in France, installed and running, of course. And that's it. That's been all from my side for the moment, just introducing the technology. And now I would like to give the word to Mario, who is the one giving real value, let's say, to this session and for the dairy industry. Mario, all yours.
Hi, Oscar. Thank you. Thank you for the introduction.
Yeah, and just warn you that there are quite a few comments, so I guess you will have some work later on in the Q&A section of the webinar.
Yeah, hopefully I can answer most of the things now, but let's see.
All right. If not, we will answer all of them via email, those that we cannot manage here during this time slot that we have booked for the webinar. Okay.
Great. So thank you. So hi everyone, and thank you for joining. I have a few slides to present the potential of HPP for dairy products. I would like to go through different applications, and maybe the most important one and the most obvious one is milk. So let's see what HPP has to offer for milk preservation. I guess we all know that raw milk has some risk, the consumption of it, because of the presence of potential hazards. You have here a list of pathogens that are linked to raw milk. Listeria, Salmonella, Campylobacter, E. coli are maybe the most common. So checking some data, I could see that between years 2013 and 2018, only in the US, 17 outbreaks linked to raw milk happened. Among them, 74 were linked to raw milk in single state, and among them, 78% occurred in states where the sale of raw milk was allowed. So there is a clear relationship. Jurisdictions allowing raw milk sale had a 3.2 greater number of outbreaks compared to jurisdictions where retail sale was prohibited. And lastly, it was observed that the jurisdictions where the sale was allowed in retail stores had 3.6 greater number of outbreaks compared to those where the sale was allowed only on farms. So there is indeed a risk, and we can see this in the news almost on a weekly basis or monthly basis. Okay, and more recently there are some also news saying that the bird flu virus is detected in raw milk. So can HPP control these pathogens on milk? So I have some slides showing the potential of HPP. This study here shows that applying HPP 6000 bar, 87,000 PSI for 3 minutes could achieve more than a 5-log reduction of the 3 main pathogens, E. coli, Listeria, and Salmonella. It is important to mention that the pathogen evolution was not monitored through storage, and E. coli studied was not the Shiga toxin producing type that regulators are demanding to control. I have another study showing different pathogens: Staphylococcus, E. coli, Salmonella, Listeria. And yeah, the bars represent a log reduction. So processing milk at 6,000 bars for 6 minutes achieve a big log reduction for most pathogens. It seems that the Staphylococcus is one of the most resistant ones, because you can see the inactivation is only above 3 logs. Okay. But this particular study again did not monitor the evolution during storage, and the milk that was used for the study was already UHT treated. This is not raw milk. This other study shows also what happens with a UHT treated milk that is inoculated with very high levels of pathogens. This is Listeria, okay? And yeah, to achieve more than a 5-log reduction, it was needed to extend the holding time up to 7 minutes at 6,000 bars, okay? But this example shows how increasing the holding time also increases the inactivation up to maximum, okay? I also have this one slide here, okay? This has nothing to do with milk, but since there is an increasing concern with avian influenza and some detection in raw milk, I wanted to show some data. So it is important to note that it remains unknown whether HPP can control the H5N1 subtype that is causing these recalls. But we have some research that suggests that the H7N7 subtype, which is also highly pathogenic, can be controlled in other matrices. So the graph here shows what happens to this particular subtype in 2 different media, fetal calf serum and chicken meat. And it seems that the virus is quite sensitive, because actually more than a 5-log reduction is achieved already processing at the 5,000 bar, 72,000 PSI for only 25 seconds. Okay, so in less than 1 minute, we have a huge reduction for this subtype. And there is also a second study. I don't have the graph here, but I can tell you that more than a 6-log reduction was achieved on chicken meat again, processing at 6,000 bars for 1 minute. So potentially HPP can also control this hazard in raw milk. So what happens when it comes to process validation? The National Advisory Committee for Microbiological Criteria for Food in the US published this document some years ago with requisite specific parameters for establishing the equivalence of alternative methods of pasteurization. And I could extract the following lines. It says that a safe harbor is defined as a recognized procedure that can be employed without further validation studies. It also says that milk pasteurization is based on inactivation of at least 100,000 guinea pig infectious doses of Coxiella burnetii, which is a pathogen, of course. And the need to revalidate should be assessed when new hazards are identified or when changes are made to the process or product. HPP, let's say, is a new process compared to thermal pasteurization. So all of these considerations apply to validate HPP as an equivalent process. What are the technical challenges? Well, there are some questions that they still need an answer. First one, is Coxiella burnetii the most resistant pathogen for process validation? This is something we don't know because there is no research. And conducting research with this pathogen is very expensive because, as you saw before, laboratories need to work with guinea pigs, and this type of studies are expensive, must be conducted in biosafety level 3 containment areas, so not many facilities can do this type of work. There is also an absence of pathogen recovery data in milk. So all data I showed earlier was only the immediate effect of HPP, but we don't know how pathogens behave after that. And there are no established protocols regarding pressure-resistant strains, milk properties to be studied. So these things need to be addressed before validating the process. Regarding other regions of the world, I have included here some guidance or assessment conducted by other authorities. So in the case of New Zealand, they have this very nice review of HPP when applied as an alternative to pasteurization. And somehow they conclude that combining high pressure with moderate temperatures around 50 Celsius or 120 Fahrenheit may achieve the 5-log reduction of pathogens in milk. They also concluded that there is no safe harbor, as I discussed before, because the available data does not support default HPP parameters for milk processing. And they also mentioned that there are some indicators missing for process verification. Why is that? Because the pressure resistance of the enzyme alkaline phosphatase makes this indicator unsuitable. This is something to consider. HPP is not efficient in activating this enzyme that is typically used to verify the efficiency of the process. The European Union also has some assessment. This was published by the EFSA, the European Food Safety Authority, and they give a very nice insight. So they concluded that checking all literature available, that the performance criteria for HPP for Mycobacterium, Listeria, E. coli, Salmonella, and Campylobacter can be achieved processing at 6,000 bar, 87,000 psi for 6 minutes. However, to achieve this performance criteria for Staphylococcus aureus, it is needed to increase the intensity of the process up to 8 minutes. Okay, so processing at 6,000 bar for 8 minutes, it is possible to achieve this 8-log reduction for the most pressure-resistant pathogen. Okay. However, this review considered that inactivation kinetics followed a linear trend, and it is very well known that with HPP this does not apply always. So this is something to consider. in this assessment. Okay, so as you saw, there is a potential for HPP to control pathogens, but what's the point of creating a safe product if the quality is not as expected? So now I present some data that shows that HPP can also preserve milk quality. This study here shows the evolution of two different indicators. In blue color, we have Enterobacteriaceae. So you can see how quickly they grow in raw milk. After 5 to 6 days, milk is already spoiled, I would say. However, processing at 6,000 bars for 3 minutes keeps counts below the detection limit through storage between 25 and 30 days. And in gray, you can see total viable counts. HPP achieves 4 log reduction of this indicator, and this delays the recovery during storage. I have another study here that shows, again, 2 indicators, psychrophiles and total viable counts. So before processing, we have very high counts, but right after HPP, 5 log after HPP, and almost a 4 log reduction, again, for total viable counts. And this reduction is more or less sustained through storage up to 22 days and 8 degrees Celsius or 46 degrees Fahrenheit. This other study shows that processing at 6,000 bars for 14 minutes keeps also stable the counts of total viable counts. As you can see, the process achieves close to a 4 log reduction, and this reduction is sustained through 60 days of storage at 6 degrees Celsius or 43 Fahrenheit. I also have this other study on raw milk processed at 6,000 bar for 15 minutes. Processing time was very high, but you can see that the process achieves, again, a 3 log reduction of total viable counts, and the reduction is sustained up to 30 days of storage at 6 degrees or 43 degrees Fahrenheit. Okay, other than bacteria, it is important to see what happens to the nutritional quality. It seems that HPP retains most of the vitamins and minerals of raw milk. This study here compared the concentration of several vitamins before and after the process. And you can see in all cases that that concentrations are somehow comparable, and in some cases even it could be detected a higher concentration in the higher pressure processed milk. So nutritional value was not affected. In the case of raw milk, there was a significant degradation after 6 days of storage. And shelf life could be extended after the application of HPP, even if we had a slight decrease of vitamins throughout storage. This was not a consequence of HPP, but something that happens to fresh or fresh-like products during storage. This study shows how HPP affects viscosity. In this case, this is goat milk. Okay, so solid bars represent different HPP intensities, and dust bars represent thermally processed milk, heat pasteurized. And the gray bar here is the reference control, unprocessed raw milk. And it can be seen that in most cases, viscosity remains closer to the original value in the case of HPP. So what happens to the appearance of the milk? HPP normally, when applied to raw and homogenized milk, increases the yellow color component. Why is that? Because pressure changes the structure of casein micelles, and this translates to a more yellowish color. Okay, you can see here the appearance of high pressure processed milk, even if the picture is not very high quality, but yeah, you can see the color is a bit more yellowish. This study shows something similar. So L, A, and B stands for the different color components. Letter B indicates the yellow color. So higher values in letter B translates into more yellowish color, and this is the case with HPP. You can see how processing raw milk at 6,000 bar for 3 minutes increases a bit this yellow component. And on the right, you can see another parameter that we call delta E. Delta E indicates how humans perceive color. So it is generally accepted that delta E values higher than 3 indicate that the human eye can perceive a color difference. This is the case with heat pasteurized milk, but in the case of HPP milk, the value remains below 3, so the color change is less obvious compared to thermal pasteurization. This study compares different sensory attributes of raw milk, raw, HPP, and thermally processed. So when it comes to flavor, people tasting the milk couldn't identify any difference between raw and HPP milk. And the differences in aftertaste, taste, and color were minimal compared to the raw control. So you can see in all cases that heat pasteurization had a bigger impact in these sensory indicators. This is also very illustrative. The graph here shows the isoreduction curves of HPP conditions that cause a 90% reduction of the activity of enzymes and the denaturation of some whey proteins. Conditions used for this representation are the same ones that cause a 5-log reduction of Staphylococcus aureus. If you remember, this pathogen is very resistant, and the line is here. So all combinations of pressure and time that align with this curve will achieve this 5-log reduction. And you can see that for all enzymes and whey proteins, they remain less affected. They still remain active in the case of enzymes, and in the case of whey proteins, lactoferrin and beta-lactoglobulin, which are here, they still remain in the native state, at least at some point. Okay, so this is also a good indicator on how HPP preserves these attributes of raw milk. There are already some companies taking advantage of the process. Vila de Patos is one of them. This is actually the first HPP milk in the world. They are based in Mexico, and they apply standard HPP conditions to extend the shelf life of milk. They have cow and ewe milk, and this product is non-homogenized. and they achieve around 30 days of shelf life. Australia is also a good example for commercial applications. The company Made by Co, they have a patented process, so they are the only ones that can apply this process in Australia. And actually, they use a back-to-back cycle. This means they apply 2 consecutive cycles of HPP to the same batch of product. With this approach, they achieve around 40 to 45 days of shelf life. They have different references of product, full fat or skimmed. And again, their product is non-homogenized. So you can see in the picture here, this nice thick layer of cream on top of the bottles, okay, because the product is not homogenized. And this process was assessed and approved by Australian authorities. So there is a scientific background to support the application. Also in Australia, we have the company Naturo. This company has the process patented worldwide. Okay, it's not only Australia, but they have the patent active in many other countries. The process combines HPP with a moderate temperature, always less than 60 Celsius or 140 degrees Fahrenheit. And again, the process was assessed and approved by Australian authorities. So they have strong scientific evidence to support the application. And the company claims that the process improves the amino acid bioavailability. It helps with protein digestion, with less intolerance and gut inflammation, and also improves the calcium bioaccessibility. Okay, so this is all I had for milk. Now we can move to cheese, okay, which is also an important application that can benefit from the process. Food safety first. This is data that I got from the FDA. So this applies to the US. And in the year 2024, we had 6 market recalls due to the presence of pathogens and 2 foodborne outbreaks related to cheese consumption. So far in 2025, I could find already 1 market recall. Okay. So which products were recalled? Different types of cheese, fresh cheese and ripened cheese. Okay. Listeria is the pathogen behind most of the recalls. But we also had some recalls due to Salmonella and E. coli. And for the 2 outbreaks we had last year, Listeria was behind one in ripened cheese, and E. coli behind the other one, also in the cheddar ripened cheese. So I have now several studies that show pathogen reduction. In this case, commercial fresh cheese was inoculated with very high counts of Listeria, and a process of 6,000 bar, 87,000 psi for 5 minutes achieved a 4-log reduction, a bit higher. But we never expect such a high concentration of Listeria. So in the study, they also tried a lower inoculum concentration, around 3 logs. And the process, you can see here, could keep the counts below detection limit almost during storage, the 15 days of storage. Okay. So this translates to a 3 to 4 log reduction of Listeria. This is another example on fresh cheese from cow milk. Okay, and the cheese was inoculated again with very high counts of Listeria at 2 different points, at 2 different stages, during the card cutting and during cheese slicing. Okay, And the process of 6,000 bar for 3 minutes could achieve between 3 and 4 log reduction, depending on the initial concentration of the pathogen. So the initial concentration was higher in the case of interior when Listeria was inoculated in card cutting, and the concentration was a bit lower during slicing. So this explains the slight inactivation observed. So this is an example on raw cow milk cheese. So the milk was inoculated with Listeria. Milk was not pasteurized. Cheese making process continued as standard. And the cheeses were ripened for 60 days. An HPP was applied in 2 different stages, on day 2 of ripening or on day 50 of ripening. And here you see what happened. When HPP was applied on day 2, more than a 5 log reduction could be observed. Okay, so Listeria counts were around 7 logs on day 2, and after HPP, counts dropped to 2 logs, and Listeria counts continued dropping as ripening evolved. Another approach could be applying HPP on day 50, and again you can see that this translates log reduction. Okay, so in the unprocessed control, Listeria could improve safety. And the same was studied with E. coli. So the same cheese was inoculated, the milk was inoculated with very high counts of E. coli, and HPP was again applied on day 2 or day 50. So when HPP was applied on day 2, close to a 4 log reduction was achieved, and the counts continued to decrease during ripening because of the sublethal damage that E. coli had. And applying HPP on day 50 already achieved more than a 5 log reduction. And you can see that unprocessed cheese, E. coli was still there by the end of ripening. Fresh cheese, this particular one was inoculated in the curdling stage, in the curdling when the milk was coagulated, but some starter cultures were also added. This means that the pH of the cheese was a bit lower compared to other products because of the starter cultures. So you can see that applying HPP achieved an immediate 6 log reduction of E. coli, and this reduction was maintained during 15 days of storage at 80 degrees Celsius or 46 degrees Fahrenheit. But HPP is not only beneficial to kill pathogens, but the process can also improve shelf life. Here you see different to bacteria growth, mainly Pseudomonas, Erratia, different bacteria, but also molds and yeasts can spoil cheese, as you can see here. Bacteria is also behind the gas formation, and gas formation is responsible for the early blowing or late blowing of the cheese, as you can see here. And bacterial growth also affects flavor and texture of the cheese. So again, some examples. This is fresh cheese, standard process, you can see here. I'm processing the cheese right after manufacturing at the 6,000 bar, 87,000 psi for 3 minutes, delayed the growth of aerobic mesophiles, as you can see here. So even after 80 days of storage, the counts were below 4 logs. So this drastically increased shelf life of this product. This is another example on fresh lactic curd cheese manufactured from pasteurized milk with starter cultures. So the starter cultures decreased the pH of the final product. You can see that the pH was 4.3. And we see here two different indicators. Yeasts, which were fully inactivated, you see no growth during 55 or 58 days of storage. In the control cheeses, you can see that they grow very quickly. And for lactic acid bacteria, again, no growth. The line overlaps here. We have a decline in the counts during storage, but applying HPP stabilized somehow the product. This is again another example on, I have already showed this, sorry. Yeah, so we have now this one on fresh cheese. This is a goat milk, okay? So the milk was inoculated with E. coli, not pathogenic, but spoilage and hygiene indicator. And we can see that applying HPP, 5,000 bar for 5 minutes, achieved an 8 log reduction of E. coli and a 3 log reduction of aerobic mesophilic bacteria. So the process is very efficient to control spoilage microorganisms. In this particular case, E. coli and aerobic mesophilic bacteria did not recover through 60 days of storage. And you can see here the pH of the product. So another example. This is a brine cheese made from raw milk, so no pasteurization stage. After cheese manufacturing, the cheese was salted in brine. And you see here the pH value of the final cheese, 5.7, and water activity 0.96. And yeah, the process could achieve a 4 log reduction for Enterobacteriaceae, same for total mesophilic bacteria, and 3 log reduction for molds and yeasts. Okay, so we can improve microbiological quality. Mozzarella is maybe one of the most famous cheeses, and the process is also efficient, keeping counts under control. So we can see here that processing at 5,000 bar for 5 minutes again delayed the recovery of total mesophilic counts. Okay, but also texture is very important in this type of cheeses, and I could see some questions in the chat about this. So this data here shows that the process has a little effect in firmness, cohesiveness, and battery texture. It is true that in our experience, firmness and cohesiveness usually increase a bit after the process, but this is something that can be addressed in the formulation. This study shows how color was affected during storage in a commercial fresh cheese. So when it comes to color components, if you remember, component B indicates yellow color. So the process slightly increases these color components because of the effects in the proteins. But you can see that the color remains very stable. This is the delta E parameter. If you remember, values below 3 indicate that humans cannot perceive color changes, color difference. And I have this last example. Okay, this explains how HPP may also help to prevent late blowing in cheese. So raw milk was inoculated with Clostridium tyrobutyricum spores. The cheese manufacturer was standard. This was raw milk, okay? And the cheese was ripened for 60 days, but they were processed with HPP on day 7 after manufacture. And you see here what happens after 60 days of ripening. So for the unprocessed cheese, inoculated with Clostridium, we can see gas formation. And same applies for very low HPP conditions, okay? So 2000 bar, 29,000 PSI, still allow some gas formation. But more intense process delayed this gas formation. So I want to clarify, HPP does not kill the spores. So if we had some spores were still there. But in this case, HPP killed the germinated spores, okay? Because those are more sensitive to the process. And in this particular case, the inactivation of germinated spores was sufficient to prevent gas formation, okay? But still, we need some controls for spores. And I have, to finalize the presentation, some other potential applications in the dairy industry. So these examples are a bit far from application, but innovation in the dairy industry, I think, needs to start here, okay? Because this is a nice example of new potential products that HPP can promote. So one potential application is to increase the yield during cheese making, okay? So what is the idea for this? So cheese starts with HPP. This means that the raw or pasteurized milk is subjected to HPP before cheese making. Why? Because this disrupts proteins. This opens the structure of proteins. So the calcium phosphate that makes caseins stable is dissolved within the water phase. And this favors the reassociation of caseins in smaller clusters, as you can see here, okay? So the protein is still the same, but it finds a different configuration in smaller clusters. And the whey proteins also link and attach to these clusters. So we are increasing the concentration of protein in the card, okay? And I have some examples to show this. So this is what happens if we apply HPP to milk before cheddar cheese making. So processing milk at 6,000 bars for 10 minutes translated in a 7% increase in yield and also a higher moisture content. So this higher yield is because of two reasons, because of the higher protein concentration in the card and because of the higher moisture that the protein network keeps. This is another example on fresh cheese, okay? So this is the reference product with pasteurized milk. So we can see the yield is around 2 kilos of cheese per 100 liters of milk. Processing the milk with HPP increased 15% the yield. So we could obtain around 14 kilos of cheese using 100 liters of milk. And applying HPP to pasteurized milk increased even more the yield, okay? And I have also this example that shows the yield during the ripening process of raw cow milk cheese. So using high pressure processed milk increased already at 10% the yield. but this increase was maintained during ripening. So of course, during ripening, the cheese was losing water. So this explains the decrease in yield. But you can see that it is always higher, the yield, if the milk was processed in advance compared to the raw milk. And there is also a second potential application that has nothing to do with cheese on milk, but the process can be used for whey valorization. So whey, you know that out of 10 liters of milk, when making cheese, we only have 1 kilo for cheese, and the nine remaining liters is whey. But the whey has proteins with a lot of value, beta-lactoglobulin and alpha-lactalbumin. So if we collect the whey and concentrate the whey using ultrafiltration, we can adjust later on the acidity and apply HPP to this concentrated whey. And after centrifugation, we have two very rich fractions of alpha-lactalbumin and beta-lactoglobulin. So this is a nice way to fractionate proteins and have a high-value product. And I have an example here to show this. So if we start from concentrated whey, in the case of bovine whey, adjusting the pH to 4.6 and applying HPP to the concentrates, you can see here a very thick pellet after centrifugation. This very thick pellet is rich in beta-lactoglobulin, but the most interesting thing is the supernatant. The liquid phase contains alpha-lactalbumin. And the values I have here show that the purity of this supernatant, okay, in alpha-lactalbumin. So this is a nice way to purify whey proteins. Same principle applies to bovine whey. In this case, the highest purity there was no need to adjust the acidity, and it was the same for a caprine whey. So no need to adjust acidity to purify the protein fractions. So in conclusion, HPP has the potential to control hazards in raw milk, as suggested by different assessments, as well as the safe history of use in Mexico and Australia, where the process is approved. However, further research is needed to identify the relevant pathogens that should be considered for process validation. Also, the application of HPP to pre-packed cheese reduces the risk associated with pathogens, extends shelf life, and enables the clean label product formulation. And there is still room for innovation in the sector. So innovative applications of HPP include the increased cheese yield, cheese ripening, acceleration, and the whey valorization. So, two things. I have to say that I am sorry because this took longer than expected, but I am happy to answer some questions if you have any, because I saw many in the chat.
Okay, thank you so much, Mario. Well, some comments are saying that it's been a very informative session, so I think no worries about timing. Let's give 5 minutes to the questions, and as I put on the chat, we will then just cover those that we didn't answer here via email from our applications team. So, for example, let's go with the very first one. Let's see it. Okay, I'm showing it on the screen. What are the packaging requirements for fresh cheeses such as mozzarella, ricotta, and cottage?
So packaging, very important. It has to be flexible, plastic, and we also have to minimize the headspace. We have to remove as much air as possible. So this could be vacuum in a cup with a top film, but vacuumed. Or we can also include some brine, some liquid solution in the cup or the pouch. So plastic, and remove as much gas as possible from the package.
Okay. Thank you, Mario. And second one, how you talk about milk and cheeses, is this applying also to yogurts?
Okay. The answer is yes, but we have to consider what happens to bacteria. Okay, in some regions, to claim something as yogurt, we need live bacteria in the product. So if we apply HPP to the yogurt, we may inactivate the probiotics in it. So this is no longer a yogurt. But the process is efficient. We can kill molds, we can kill yeasts, and other spoilage microorganisms. So this, I guess, this depends on the final application and the region where the product is manufactured.
All right. Another one, is the process effective for sliced cheese?
Yes, yes, of course it is. You explained it very well. So the process is isostatic. So size, shape are not critical factors. One thing to consider maybe is that the cheese slices after the process may attach to each other. So to avoid that, we encourage to put some plastic sleeves between the slices. Okay, so this will make a separation very easy after opening the pack.
Okay, and then the last ones, both related. So how effective is this for cheese with the spices? And the other one that is pretty much the similar is, how effective is this technology on dried spices?
Yes, good question. So spices are very well known because they are highly contaminated. Okay, it's very easy to preserve spices because they are dry, so nothing will grow there. But as soon as we put spices on high water products, the microorganisms that are present in the spices can grow because we are giving the nutrients, the water they need. So HPP is effective to control this growth in cheese with spices because HPP is efficient in activating bacteria, as you have seen. But HPP is not efficient in activating bacteria on dry spices. The reason is that we need some water to transmit pressure. We need very high water activity for the process to be efficient. So applying HPP to the dry spices makes no sense because we have no inactivation because of the low water activity. But if spices are used as ingredient in cheese or ready meals, whatever, then the process is very suitable, I would say.
All right. Okay, so well, many questions that we cannot answer right now, but again, we cover it via email, no worries. I would like to thank you, Mario, for your great value, the great value you offered to this session. And yeah, sorry, I was saying that I would like to end up well, thank you, Mario, for the great value you offered to during the session. Sorry that I think you had some connection problems that just took a couple of seconds. Mm-hmm. So thank you, Mario. And I would just like to finalize the session with a few slides about Hiperbaric. And so we are almost 200 employees with more than 400 installations worldwide, and that makes 65% of the global market shares. These are our offices. We are present in Mexico, the US, Spain, Shanghai, and also Australia. And this is what I would like to mention before ending, and that we have pilot plants or our HPP incubator in Spain, USA, and China. and we are open to make free testing for those requiring it, to make some trials with the products, the packaging, whatever. And Mario and the applications team will be more than glad to receive those products and to guide you with HPP parameters and to make the different tests you would like to do with your products and to check the effectiveness of HPP to your products. And that's it. Applications team with 6th grade colleagues covering all these needs. And that's been all from our side. We hope you find this session really informative. And that's it. Just stay tuned, because soon we'll have the HPP Innovation Week, for example, and also some webinars yet to come. So stay tuned, follow us, and